Okay, so some hints on this paper. Questions relating to scalar or vector. Oh, first of all, this is the specimen paper. This is a sample specimen paper for the Unit 1 Mechanics and Materials. So, scalar or vectors, remember vectors have two numbers. One number gives you the size and one number gives you a direction. So that's what you've got to be looking at. Scalars are just going to be one number only, okay? As a lava leaves a volcano, it cools down. Select the row of the table that correctly describes the effect of a lower temperature on the viscosity. In general, the rule is that as you higher temperature, things get more runny. Think of honey, heating honey up. Things get more runny, so that is a lower viscosity. And you've got to think about whether that will make the flow rate decrease or increase. Okie dokie. Right, let's crack on. Car is travelling at velocity v. The driver applies the brakes and the car decelerates until it comes to rest. Work done. Okay, so first of all, the work done, you're going to know that is equal to the force times distance moved. You also know that the work done is going to be equal to the kinetic energy that is lost. Okay, so there's a couple of different ways of kind of working out depending on what they give you. Now they're giving you v squared, 1 over v and 1 over v squared. So they're going to give you something which relates to v squared or v. Now, which of these you use is up to you. You can either use the idea that kinetic energy, which has got a formula of half mv squared, is equal to the work done. Or you could use the force. Do you know the force and do you know the distance? Well, it's not going to be as easy for you to do that. Distance and the velocity, you can sort of do it, but it's a bit more complicated. So you might be better off to use the kinetic energy one and then work out the relationship between the two. Next question relates to forces. And the force acting in the box are shown. So we've got a contact force and a weight. These forces are equal and opposite. According to Newton's third law, the box will exert a force on the man. Oh, okay, so this is an interesting one. So the thing to remember with Newton's third law, Newton's 3, that the forces or the force pairs are equal, opposite, and they act on different bodies. So this is not a Newton 2. Newton 2, we're looking at all the sum of the forces are equal ma in relation to the particular body. So Newton's second law would be this thing, looking at the sum of all the forces being equal to ma. And Newton's third law is not at all. It's saying, well, if the man is, this is the man here, if the man is pulling with a force there, then an equal and opposite, but on different bodies, will be the box exerting a force on the man. So that's kind of enough to tell you, not too much. Right, photograph shows the flow of air around the wing of an aeroplane. Usually we're looking at straight lines being laminar flow, smooth flow, where things like Stokes' law apply, and messy sort of other areas being turbulent flow. That's the sort of thing that we're looking for. Turbulent flow is when all these lines cross and sort of, bundle into each other. So the thing about laminar flow is that the speed of the air at a particular point is going to be the same. So if we actually sort of draw a cross section at any point here, the speed of that bit, speed of these bits, speed of this bit is constant over time. Okay, and this bit, the speed at any one point is changing. So that might be enough for you to have a crack at that question. Question 6, the ball is dropped from a window. Always you should sketch these things out. And it takes 1.6 seconds. T equals 1.6 seconds. Which of the following is the height of the window? Well, you're going to have NS is going to be related to that using a Suvat equation. And the one that we always have is we always have EA, which is equal to minus 9.81 newtons per kilogram, because that's acceleration due to gravity. You've got to think of which Suvat equation would be good. Well, it's distance, it's A, and it's T. And so something like S equals UT plus half AT squared. Dropped means the initial velocity is 0, so we can ignore these bits, and then you're going to be able to work out a way of calculating S. In this question, increasing forces were applied across the ends of a wire and the corresponding extensions are recorded. The force extension graph was plotted for the wire. Okay, so you've got to work out what's going on with the elastic limit. Until that point, until the elastic, so FC is the elastic limit force. An elastic limit force is if force is greater than that, the thing won't return to its original shape, is the idea. Okay, now Hooke's law is not quite the same as elastic limit. Hooke's law is proportional. Hooke's law, F is equal to minus kx. That means that the extension, the stretch, is proportional to the force. And that would be, on a graph, that would be a straight line. So if it's bending, it's no longer Hooke's law. So that should be enough to get you cracking on that question. The second one, the force on the wire was then decreased and the corresponding extensions recorded. The values were plotted on the same axis. Which of the following is the correct graph? Okie dokie. Right. And the question on this is you've got to watch out for. Okay, so it's the same information. Okay. Right. So you've basically got to sort of kind of work out, well, what's the general pattern of what's happening on these sorts of things? And the general pattern on these sorts of things is that if it's not going beyond the elastic limit, then you've got something which is kind of nice and smooth. If it goes beyond the elastic limit, then what you've got is something which is, well, when the force is removed, if it's gone beyond the elastic limit, then it won't be the original length anymore. And so the force actually does go, in this one, does go beyond the elastic limit. So that means it won't return to its original position. So this one is going to 0 extension. This one is going to 0 extension. So it's not these two. So it's going to be either this one or this one. You've got to work out which seems to be the most logical. And this one is an interesting one because this one is saying the extension doesn't change even when you take the force off. It doesn't change at all. It doesn't reduce its extension even when you take the force off. And this one says, well, you take the force off and then it kind of does reduce its extension a little bit, but doesn't go back to its original length. So your guess is as good as mine. Well, hopefully by now it is. Question 9 relates to a practical determining viscosity of a liquid. Now, small metal sphere, radius r, sphere, small, and it's going to be dropped in the center of the liquid and it's going to be moving slowly. Which are the best two elastic bands to use? Well, you want to measure the terminal velocity And the thing to remember when you're designing an experiment is the ball doesn't reach terminal velocity instantly. So you want to give the ball a chance to reach terminal velocity, and you also want the distance that you're measuring the terminal velocity to be kind of quite big. So I'm going to let you think about that. Excellent. Okay, and let's look at the options that they've given you. They haven't made you choose between any tricky ones. They haven't said 2 and 3 or 2 and 4, which might be a little bit of a choice, tricky one, yeah. Best two elastic bands to use. Okay, question number 10. The sphere is made from a metal of density, blah, 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 and the liquid has density this. So, which of the following, okay. So what you've got to do in this case is you've got to say, well, what's happening? What's going to be the force down? The downward force is going to be due to the weight, which is, okay, the weight of the sphere, which is equal to the mass of the sphere times the acceleration due to gravity, and the mass of the sphere is equal to the volume of the sphere times the density of the sphere. So that's what you're going to get. And opposing the motion, you've always got drag, and drag is the well, it's Stokes' law, and you should know what that is. I'm not going to tell you what that is, but that does come in the exam. You do actually get that. So Stokes' law is going to be going up, but there'll also be the upthrust, and the upthrust is due to how much liquid we're kicking out the way. So we're going to be kicking some liquid out the way when our sphere is there. It's occupying a certain volume, so it's occupying a certain volume, the volume of the sphere still, but this time the upthrust is equal to the volume of the liquid that's kicked out of the way. So it's the same volume of the sphere, but we're interested really in the weight of the liquid. Now the weight of the liquid is the density of the liquid times the volume of the liquid, which is the same as the volume of the sphere. And then of course you've got the acceleration due to gravity. So that should be enough for you to kind of work out which is right. And that's the multiple choice questions. Okay.